Hello everyone and welcome to MV Tutors. I'm Solo and we'll be looking at the chemistry paper. Alright, we're going to tackle the first question. I hope you wrote well, and if you didn't, I think this was a good way to see how the final exams are going to be. But the general trend has been that prelims are harder than the finals. Okay, so yeah, hopefully it didn't ruffle too much of your feathers and that you're encouraged to study more. You're almost there. Okay. Alright, so don't forget the drill. Please do like our videos and subscribe to our channel, and also tell your fellow classmates about our channel. We are aiming to get 2,000 subscribers. Right now we're at 1,420. So yeah, let's work our way to 2,000 and then we'll increase as time goes. But anyway, without wasting any of your time, let's get straight to question 1. Alright, so 1.1 says, consider the condensed structural formula. Okay, I don't know about you, but I like having the structural formula like with its branches and so forth, so that I see what exactly is happening. Okay, so we have the first carbon with 3 hydrogen atoms, the second carbon, which is or will be double bonded to oxygen, and then you have the final carbon with its hydrogen atoms. Okay, so yeah, now it says identify the name of the functional group of this formula. When I see this, I think aldehyde, ketone, but aldehyde has a double bond at the end, so it must be a ketone. But guys, that is not a functional group. Okay, the functional group of a ketone is actually the carbonyl group. Okay, so that will be option D. 1.1 will be D. Yeah, because if you said ketone, that is actually a homologous series, not the functional group. Okay, so now 1.2. Which of the following is the empirical formula of 1,2 dichloroethane? So ethane has 2 carbons and we are dealing with an alkane, right? And then on the first and the second carbon you have chlorine, okay? And the rest are just hydrogen atoms. I'm not going to put them in, they're time consuming. All right, and then so if you were to write down the molecular formula, okay, so you would have 2 carbon atoms, all right, 4 hydrogen atoms and 2 chlorine atoms. So that would be your molecular formula. Your empirical formula is like the simplest you can get it to be. Okay, so if I divide by 2 throughout, I would get CH2Cl, and that would be your empirical formula. And we see CH2Cl, that is B. Okay, and then 1,3. Consider the structural formula of the organic compound below. Okay, I'm gonna rewrite it or redraw it. Okay, because when it's like this, it's like, I'm not really gonna change much, but I'll say this. So you have your first carbon, right? Then you have your second carbon, which is double bonded. Then you have your methyl group. Okay, it's double bonded to another carbon. And then you have this carbon that has a methyl group. Well, firstly, we need to check the longest carbon chain before we go and say it's a methyl group. So, 1, 2, 3, 4, 5. Okay, so it's 5 carbon atoms in the longest chain. Even if I start in the carbon on top, it's still the same. Yeah, basically the longest chain, 5 carbons, right? And we have a double bond, so it's not pentane or whatever. It has to be pentene. Okay, so pent something in. Now we need to see which way are we counting. Are we counting from here, 1, 2, 3, or are we counting from here, 1, 2, 3? Okay, I would look where the double bond is. Okay, so it's on the second carbon, so I will count from left to right, not right to left. So that will be 4 and that will be 5. So I know pent 2 in. All right, And then I have carbonyl groups, all right? No, what did I say? I have methyl groups. Okay, so we have the first one here on carbon 2, and I have the third, so I have the first, the second, and the third on carbon 4. Okay, so 2, 4, 4, because it's 3 of them, it will be trimethyl. Okay, I didn't leave space for myself. So trimethyl pent 2-ene. Okay, so if you look here, 2, 4, 4 is C and D. And then we have trimethyl, yes, pent 2-ene, because we're counting from left to right. So pent 2-ene, and that would be C. Okay, and then we go to 1.4. From the following options, choose the one that best explains why catalysts are so extensively used in chemical reactions. So you think to yourself, what does a catalyst do? Well, basically, a catalyst, if you have your energy diagram there and you have whatever reaction, this would be your activation energy, right? What a catalyst does, it lowers the activation energy so that your reaction can occur faster. So a catalyst would come, lower your activation energy, and the reaction will happen a lot faster. The rate of the reaction will be quicker. So let's see. Catalysts can be used to drive the equilibrium in the desired direction. Catalysts decrease the reverse reaction. Catalysts have no effect on the reverse reactions. Catalysts cause the forward and reverse reactions to proceed at a faster rate. So we will go with D. Okay, 1.5. Study the following graph and match label X from the following choices. Okay, so activation energy, we just discussed it. It's basically the area between, or rather the length, the height between, in our 1.5 graph, 100 and X. So if this was X and this was 100, that is the activation energy, the difference between the two. Now B, activated complex, I'll have to admit, I mean, I saw activated complex, I'm like, yes, and then I'm like, activation complex, and I'm like, I know it's not activated energy. So is it activated complex or is it activation complex? All right. And if you go through your notes, you will see that it is activated complex. Okay, it is B, past tense, activated complex. So X would be your activated complex. It's not in the present tense. It has been activated. So remember, past tense, be activated. Okay, and then we get to 1.6. The equation below represents a chemical reaction at equilibrium in a closed container. So we have hydrogen gas, we have iodine gas, and then now we have hydrogen iodide. Okay, and our reaction is exothermic because your enthalpy is less than 0. Now it says, which of the following changes will increase the yield of hydrogen iodide in the above reaction? Remember, if you have an exothermic reaction, when you decrease the temperature, you are increasing, the yield of your products. Okay, yes, so it's forward favored, basically, increase the yield of your products. Okay, if you had an endothermic reaction, if you were to increase the temperature, then yes, the yield of products would be high, but we have exothermic, so we want to decrease the temperature. Now, when we look at option C and D, which talks about pressure and volume, for you to determine where it will be favored, where your reaction will be favored, you have to look at the amount of moles on each side, on the reactant side and on the product side. So on the reactant side, you have 1 mole of hydrogen gas, 1 mole of iodine gas. So you have 2 moles on the reactants. On the products, you have 2 moles of hydrogen iodide. So they're balanced. So it doesn't really make much of a difference. So I'm not considering C and D. I will look at A and B. And because we have exothermic, we will go with decrease in temperature. Okay. And 1.7. All right, which of the following solutions, each of concentration of 0.1 mole per cubic decimeter, so the concentration is constant, which has the highest pH? Okay, guys, you know, so 7, that's where you have your base, the highest pH 14, the lowest, I don't know whether to say 1 or 0. Probably 0, but this is where your acids are, right? And that's where your bases are. You guys can comment below to remind me. Does it start at 0? Does it start at 1? I think it's 0. Yeah. So if we're looking at something that has a high pH, we're looking at a base here. Okay. So the first option, we have nitric acid. So that's out. Second option, we have ammonium chloride. Ammonium chloride is actually, it is derived from when you have hydrochloric acid and ammonium hydroxide. So ammonium hydroxide is like a weak base. So if you have titration between a strong acid and a weak base, your final product will be acidic. So ammonium chloride is an acidic salt. Okay, so still pH can't be high because it's acidic. Now sodium carbonate. Carbonates are bases, weak bases, but bases nonetheless. So far that's the only base we have. D, we have yes, we have Cu. Cu, we know, acid, weak acid. So the only base that we have in this case is C, okay, the carbonate. And that will have the highest pH purely because it's a base. Is it a strong or a weak base? It's a weak base, but it's a base nonetheless. So we'll go with C. And then 1.8. A solution of ethanoic acid or acetic acid is titrated against a standard sodium hydroxide solution. So we have a weak acid. Okay, ethanoic acid is weak. Your carboxylic acids in general are weak. All right, and then we have standard sodium hydroxide. Sodium hydroxide is a strong base. So once this titration occurs, we are expecting our answer to be a base. All right, and if it's a base, it is in between 7 and 14. Okay, ethanoic acid is a weak acid. Okay, because it's a weak acid, we are expecting an answer or a pH maybe closer to 7. Okay, so ethanoic acid, it's closer to 7. Then you have your sodium hydroxide, which is probably closer to 14 because it's a very strong base. So what pH are we expecting from this titration? I think we'll be expecting an answer closer to, I don't know, maybe 10, 12. Yeah, I don't know. But a high pH, okay? So if I look then, so it says which of the following indicators would be the most suitable for this titration? I will be looking at answers that are higher than 7, a pH of 7. So we have phenolphthalein, which is between 8.3 to 10. We have methyl orange, we're not considering it, that is acidic. We have bromothiamyl blue, it's an option, all right? And then D, universal indicator. I don't want to be using that because I don't want to be confused once I use that indicator. So I will have an option between A and C. But because we had a strong base, guys, which has a pH closer to 14, and we had a weak acid, which has probably a pH closer to 7, I am most likely leaning towards option A, phenolphthalein. Okay. I hope you got my trail of thoughts there. That is me in an exam situation. Okay, 1.9, we are almost there. Chemistry is flowing. Which of the following correctly gives the direction as well as the medium in which electrons move in a galvanic cell? Galvanic cell, remember that's the voltaic cell, where you have your salt bridge. You have your two compartments, your salt bridge in between, your two electrodes, and your battery. No, we don't have a battery here. Your voltmeter, hence voltaic acid. Okay, here we have your anode, right, where oxidation occurs. Here we have your cathode, where reduction occurs. Red cat. Anyway, so it says, where do the electrons flow? In which direction? Okay, direction as well as medium. Okay, your electrons flow here, guys, right? And they flow from the anode to the cathode. So we know it's from the anode to the cathode, right? So we are looking at B and D as our options. Now, are the electrons at the salt bridge? No, they're at the external wire. So anode to cathode external wire, and that would be B. Okay, and then we get to 1.10, where it says, which of the following half reactions occurs at the cathode during the electrolysis or electrolysis of a solution of concentrated sodium chloride? Okay, so if you think electrolysis or electrolysis, I've actually covered this in the lessons, practical applications of electrolysis or electrolysis. So I'm going to refer you to that video. But what is the answer? So basically, I'm going to just draw a simple diagram, which is not really fully correct. Hence, I'm going to refer you to that video. So you know, in one beaker, you have both your electrodes where you have the anode this side and you have the cathode that side. And you have a power source, okay? And you have your solution. So this time, you have a solution of sodium chloride, okay? It will have dissociated. Basically, you would have your sodium, and it's in water, all right? So water would have dissociated to hydrogen atoms and hydroxide, and then you have sodium chloride, so sodium ions and chloride ions. Basically, this is your positive terminal, negative. So your negative ions, chloride, they basically go to the anode, and then you end up having chlorine gas. Hydrogen gets attached to the cathode, and then you have hydrogen gas that basically flows. So you have chlorine gas and hydrogen gas that basically escape, all right? But yeah, I'm not going to go into that much details. I want you to watch the video because I explained it quite nicely there. But basically, the question says, which of the following half reactions occurs at the cathode during the electrolysis of a solution of concentrated sodium chloride? Okay, so the answer would be D in this case. And so why is it D? I'm going to show you where you can see. Yeah, so if you go to playlists for the chemistry lessons towards the end, if it's not the end, yes, it is, yeah, electrolytic cells, okay? And basically, I talk about the practical applications. Let me just pause. What happened, Manji? When technology fails. And you are like, what the hell? But basically, my goodness. Okay, there we are. Yeah. What do I want? I want to make it a big screen. Sorry guys, this was supposed to go so quickly, but it is not. So let's try again. Here we are. I want to actually show you this. I think it's at about 13 minutes. Guys, it's wrong. I think I'm gonna have to more. There we are. Sorry it took so long. So this is like at 30 minutes 45 seconds, the chlor-alkali industry or chlor-alkali industry. That is basically where I explain what would happen during the electrolysis of sodium chloride, and what happens actually at the cathode as well. What are we expecting the half reaction to be at the cathode? Okay, and you will find the answer right there. Okay, so yeah, this is where we're gonna end question 1 for today, but the answer is D. Watch that video and check out how I explain it. Katimaketa, guys. Okay, we have these videos for you guys to watch. So yeah, that's it from me. Don't forget to like our videos, subscribe to our channel. We are aiming for 2,000 subscribers, and I will only release the following questions, question 2, 3, 4, and the rest once we reach 1.5, and then we release question 2, 3, 4, and then we'll get to 1,600 subscribers, release more. So go out there, scratch my back as I'm scratching yours. Alright, bye. Hello everyone and welcome to MV Tutors. I'm Tolo and I am continuing with you chemistry. So looking at question 2 at this moment. I hope you're all doing good, and thank you for liking our videos, thank you for subscribing, thank you for telling and spreading the word to your peers, your classmates. Continue doing so, liking, subscribing, notification bell, everything. Okay, so let's start. Question 2. It says the following types of formulae represent organic compounds. Study the table below and answer the questions that follow. So before I normally answer the questions, you know me, we go through the table, we see what's what, and then when we answer, things just flow. You know, because we have some time to discuss. We're not in a test situation where we want to go straight into the questions, right? So let me take you through it. Compound A, all right, I see 3 carbon atoms, so prop something. Then at the end, I see an OH group. So I know I'm dealing with an alcohol, all right? What kind of alcohol is it? It is a primary alcohol because the carbon attached to the OH group has only one other carbon attached to it. Okay, so it's a primary alcohol. And what is the name of this primary alcohol? It would be propanol. Let me put it, primary alcohol, which is propanol. There's no need for me to say propan-1-ol. But I guess you can. Propan. The fact that it's a primary alcohol means it will be propan-1-ol, but let's just do it. Let's just put it there. Okay, B. I see a compound, okay, where I have a carbon atom double bonded to an oxygen. Okay, so when I see that, I'm thinking ketone, aldehyde, carboxylic acid. Then I see what else is it attached to. If it was attached to an OH, I know it would have been a double bond to oxygen and also a bond to OH. I know I'd be dealing with a carboxylic acid, but it's just double bond to oxygen and a single bond to oxygen. And we're like, okay, it cannot be an aldehyde, it cannot be a ketone. What else can we have? And then I see, man, there's another, region in the left, another region in the right, left. Ooh, my goodness. So we have an ester. We have an ester. Now I don't know the difference between my left and right. We have an ester, okay? And now you need to ask yourself, which side of the ester is a carboxylic acid and which side is an alcohol? Well, I think a good way to see it is, where is this double bond attached to? Okay, remember before you had an OH, then so this would be like your carboxylic acid. Ooh, why am I writing carboxylic X's? Carboxylic acid. On the other side, you would have your alcohol. Okay, so you'd have OH, something like that. Yeah, H2O. So in the middle, you would have H2O that you would take out, and so you have the coming together of a carboxylic acid and an alcohol. And then once an ester forms, water is also a product. Okay, so if we take H2O out, then, it becomes an ester. But before an ester forms, you would know there's a part where you have an alcohol and a part where you have a carboxylic acid. And the part where we have the carboxylic acid is where we have 3 carbon atoms. And that would be propanoic acid, right? Propanoic acid. Yeah, and then the alcohol part, it's just one carbon, so that would be methanol. And what does it produce? What is this ester? This ester would then become, when we name an ester, we start with the alcohol. So when I sketch it, I like putting the alcohol first, then the carboxylic acid, but it doesn't matter. When you name it, start first with the alcohol. So you would get methanoic. No, I'll be lying. Now I forgot how we name esters. We have propanoate, methyl propanoate. Yo, when it escapes your mind, methyl propanoate. Yes, my baby. You're back. Okay, okay. I can see you. Okay, bye. Now, yes. So that is the ester, methyl propanoate, and then C. There is our coup. C, double bonded to oxygen and another bond to OH group. So we have only 2 carbon atoms, so that would be ethanoic acid, because they're just 2 carbon atoms. Okay, ethanoic acid is part of the carboxylic acid group, functional group. And then D, okay, when I have a structure like that, I want to put it in a structural formula. So I have CH3, then I have another C bonded to an OH group, and then bonded to another hydrogen. And then we have carbon with 3 hydrogen atoms. So we have another alcohol, and I hope you can see that this alcohol is a secondary alcohol, right? Because the carbon attached to the OH group is also attached to 2 other carbons. So hence a secondary alcohol. We have 3 carbons, so it is propanol, right? But way propan 2-ol. Yes, propan 2-ol. Alrighty, and then E, we have 2,4 dimethyl pent 1-ene. So I know pentan means I have 5 carbon atoms. And then on the first carbon, I have a double bond. On the second carbon, I have a methyl group. On the fourth carbon, I also have a methyl group. And yeah, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that is our 2,4 dimethyl pent 1-ene, and that is an alkene. Okay, because we have a double bond there and it is unsaturated. F, we have 2-methyl propan 2-ol. We have another alcohol with 3 carbon atoms. On the second carbon, we have a methyl group. Again on the second carbon, that's where we have our OH group. And yeah, we can put all the other H atoms. That is a tertiary alcohol. I hope that you saw it. Why? Because the OH group, the carbon attached to the OH group, is also attached to 3 other carbons. You see that, right? Tertiary alcohol. And that is F, 2-methyl propan 2-ol. And then G, we have a lot going on. So we're going to look at the longest chain. So if I go from left to right, I can go to the carbon up there. All right, I still have 6 carbons. 3, 4, 5, 6. I can go to the carbon at the bottom. Okay, I still have 6 carbons. So the longest chain is 6 carbons, right? Consists of 6 carbons. So we have hexane because they're all single bonds. I don't have any double bonds, but I see that we have a bromine atom there. So this is actually a haloalkane. So it's not just an alkane, it's a haloalkane. If we were to name it, where would you start numbering your carbon atoms? Would you start from the side closest to the halogen or closest to the branch? Yes, closest to the branch. So you're going to start numbering from right to left. So on the second carbon, you have your methyl group. Actually 2 methyl groups, so it's going to be 2,2 dimethyl. Okay, but when we name it, what do we start with? Do we start with the methyl groups or do we start with the bromine atom? Well, you have to name them in alphabetical order. So B comes before N. So it will be, where is the bromine? On the 5th carbon. So it will be 5-bromo. I don't know if everything will fit. Probably not. So 5-bromo. Then we have 2,2 dimethylhexane. Okay, so the numbering of carbons start at a branch, but with the naming, you have to look at alphabetical order. Okay, now we can start answering the questions. I won't be writing the answers down. I'll be like, yeah, that's the answer right there. We discussed it. Not fair enough. So 2.1, it says, from the table above, consider compound B. Compound B is our ester. Okay. Now it says 2.1.1, the homologous series to which compound B belongs, while compound B belongs to the esters, right? That's the homologous series. Okay, so 2.1.1, ester. 2.1.2, the IUPAC name of compound B, I did give it to you guys there. It will be methyl propanoate. Okay, maybe I should write it down. So it's an ester. 2.1.2. Okay, 1.2, that is methyl propanoate. And then 2.2.1, so it says an alcohol and an acid are heated in the presence of concentrated sulfuric acid to form compound B. Okay, the role of the concentrated sulfuric acid in this reaction, well, it speeds up the reaction, therefore it is a catalyst. And then names of the alcohol and the organic acid used to prepare the compound. We did say that the alcohol there is methanol. Okay, and the organic acid would be propanoic acid. Propanoic acid. And then 2.2.3, name of the type of the reaction that is taking place. Well, in producing an ester, we say that it is called esterification. Okay, we're still going. Okay, 2,3,1. So, from the table above, consider compound C. What happened at C? C, we have ethanoic acid. Okay, that is the carboxylic acid. Now, what does it want? It says, write down the name of the functional group of compound C. So that is basically carboxylic acid. We just said it now. Okay. Functional group, ne? Yeah. Carboxylic acid. And then 2,3,2, it says to which homologous group does... No. Sorry. The first one, I talked about the homologous group. Yeah, sorry. So the functional group is actually the carboxylic group. Ne? Sometimes I also confuse myself. But when it comes to the homologous group, that would be the carboxylic acid. Okay. And then 2,3,3. Differentiate between the terms functional group and homologous series. We were coming to that, weren't we? Okay, so decided to take a small break and write down. So what is the difference between the functional group and homologous series? Well, with the functional group, the group of atoms, it's basically a group of atoms that determine the physical and chemical properties of the group of organic compounds. Okay, so it has to do with the chemical and physical properties, whereas a homologous series, it is a series of organic compounds that can be described by the same general formula. Okay, if they belong to the carboxylic group, then they will have the COOH. Okay, that's how we know carboxylic acids. So that is the difference, and it's only 2 marks. Now we can go to 2.4. It says from the table above, consider compounds A, D, and F. Okay, A, D, F. A, we had the primary alcohol, propan 1-ol. D, we had the secondary alcohol, propan 2-ol. And then F, we have a tertiary alcohol, which was the methyl group and the alcohol, the OH group on the second carbon. I think they gave us the name there. F, which is 2-methyl propan 2-ol. Okay, now it says write down the homologous series to which they belong. We just said the homologous series is described by the same general formula. Okay, so it is in the group of alcohols. Homologous series called the alcohols. Where am I? 2.4.1, 2.4.2. Compound A and D are isomers. So what type of isomers will they be classified? Remember, A was propan 1-ol, D was propan 2-ol. So the position of the OH group changed. So they will be positional isomers. Okay, and then 2.4.3. Draw the structural formula of compound F. I did draw it. Okay, but let us just make it a little bit more elaborate. Okay, so we had 3 carbon atoms, right? And in the second carbon, we had the OH group. Remember OH, we don't put it together. We need to show the line, the Lewis diagram, basically for it, with the lines, not the dots. Okay, so the first carbon, we had the 3 H atoms. And the second one, we had a methyl group. Okay, so we also need to show structures there. And then the last carbon. Okay, it's basically that. And now 2.5, we're almost there, guys. Write down the IUPAC name of compound G. I'm going to copy and paste. There we have it. We discussed it quite in detail. So yeah, it is the 5-bromo 2,2-dimethyl hexane. Okay, so that is the name. And then what did it say now? What do they want for 2.5.2? Okay, so 2.5.1, 2.5.2. Write down the structural formula of compound E. I'm sure we did that as well. So compound E, that is where they said the 2,4-dimethyl pent 1-ene. Okay, I'll do it again. Okay, so we have 5. All right, 2 with its methyl group. 2,4. Okay, 2,4-dimethyl pent 1-ene. Okay, 1, 2, 3, 4. 1, 2, 3, 4. No. We already have 4 bonds around that carbon. So 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. And we are done. We are done with this long question. But to be honest, I love organic chemistry. I feel like this is where you should be banking your marks. That is where you should be like hitting them hard. So I hope you enjoyed the session. You learned something. If you have any questions, please comment down below. If you found anything wrong in something that I wrote, or you're uncertain about something, again, please comment. And don't forget to like our videos, subscribe to our channel, click on the notification bell so that you know when we post the next question. And don't forget to share this information with your fellow classmates. Okay, bye. Hello everyone and welcome to MV Tutors. I'm Tsolo and I'll be looking at question 3 with you guys from paper 2 of the Gauteng prelim exam. Alright, so don't forget to like our videos and subscribe to our channel. Please tell a friend, classmate, whoever's in matric, grade 11s, this is what you headed towards. Okay, so we're still busy with organic chemistry, and let's just see. Okay, so it says, study the following two organic structures and answer the questions that follow. Okay, let's look what is happening at A. We have a carbon atom double bonded to an oxygen atom as well as hydrogen on the other side. So, and then we have a similar structure for B, but the double bond to oxygen is on the third carbon, the one in between. All right, so we can see from A that we have an aldehyde, okay, because the double bond is at the end. So whether it's at the beginning or the end, it's still at the end, okay? So it's an aldehyde. There's no need for you to say aldehyde, whatever, if we're naming it. So we have 5 carbon atoms, so it'll be a pentanol. So that, yeah, you won't say pentan 1-al. Ooh, aldehyde. Wow, tools. Okay, and for B, we have a ketone. Okay, so if your double bond to oxygen is somewhere in between and not on the end carbons, then you have a ketone. So it will be what? 5 carbon atoms, so it will be pentanone, or pentanone, but it's on the third carbon, so pentan 3-one. Okay, yeah, so that's what it is. Now it says 3.1.1, compound A and B are functional isomers. So we need to define the term functional isomer. So a functional isomer, remember an isomer has the same molecular formula, but the difference is that they are from two different functional groups. Okay, yeah, so same molecular formula but different, functional group. Okay, the ketone is from the carbonyl group and the aldehyde is from the formal group. Okay, so different functional group. Cool. I don't think they need you to mention ketone is from carbonyl and aldehyde is from formal, but I guess you can always mention that. Okay, and then it says write down the IUPAC name for of compound B. We already spoke that it's a ketone. We have 5 carbon atoms, so it's a pentan something, pentan 2-one, because it's a ketone. All right, now it says, how does the boiling point of A, okay, so A, remember, we have an aldehyde. How does the boiling point of A compare to that of pentan 1-al? Okay, so aldehyde, we had pentanol, right, and our alcohol there, which is pentan 1-al. So instead of, at the end, instead of having that, the alcohol would have okay, the alcohol would have an OH group. So it says, how will the how does the boiling point of A compare to that of the alcohol? Okay, so aldehyde, it has a weaker intermolecular force compared to alcohol. So alcohol will have a higher boiling point, all right? But when we write our answer, we would see that it would be lower than. So aldehyde would be lower than the alcohol. And then it says, explain your answer. Okay, so like I said, an aldehyde has a weaker intermolecular force compared to alcohol, because alcohol has that OH group, okay, and the forces there, you have hydrogen bonding for alcohol. So I'm gonna just continue. So here you have hydrogen bonding, which is quite strong, okay. You have a higher boiling point, you have a higher melting point, but your vapor pressure is quite low. On the aldehyde, on the other hand, you have a dipole-dipole bonding type of bonding. Dipole-dipole bond, or dipole-dipole force, sorry. Okay, and as a result, you have a lower boiling point in comparison to the alcohol. You have a lower melting point, and you have a higher vapor pressure. Okay, so yeah, referring to the intermolecular forces present. So the one is dipole-dipole force, other one is hydrogen bonding. So the bonds for hydrogen bonding are quite strong. So you have strong intermolecular forces, whereas here you have weaker compared to the alcohol intermolecular forces. Okay, next question. How will the vapor pressure of compound B, okay, so compound B, that is the ketone, how will the vapor pressure of compound B compare to that of pentane 1-ol? Okay, so we're still comparing to an alcohol. Again, here you have hydrogen bonding. Okay, and here you still have your dipole-dipole. Because the ketones and the aldehydes are the same. It's just, well, not really the same. They are isomers, functional isomers. So the properties are quite similar, chemical properties. So yes, for ketone, you still have dipole-dipole. Alcohol is still hydrogen bonding. Again, same reasoning as the other one. You have stronger molecular forces. So, stronger intermolecular forces, but it means then your vapor pressure is quite low for the alcohol compared to the ketone. Let's just read the question again. How will the vapor pressure of compound B? So the vapor pressure here will be higher than, okay? So, higher than. And explain the answer fully again. We would say, because we have dipole-dipole forces, the intermolecular forces are weaker than that of the alcohol, therefore your vapor pressure is higher than. Okay. My son is watching something that's loud. Let me just pause and go. Okay, sorted. Yeah, now 3.2, it says learners use compounds C to E to investigate one factor which influences the boiling point of organic compounds. So if you have a look at C, all right, and if you were to draw the structural formula, so we have CH3 and you have CH2, and you have CH2, and then you have CH3. So this is an alkane, saturated butane. Yes, butane. Butane. I want to say butanol and butanol, and no, it is butane because you have an alkane. So D is the same, but it just increases by 1. So we have pentane, and E also increases by, yeah, so we have hexane. So these are all alkanes, and we can see that moving from butane to hexane, the boiling point increases, right? So as the chain gets longer in your alkanes, the boiling point does increase. Okay, that's the trend that we're seeing. Now it says 3.2.1, we should define boiling point. So boiling point, I would say that it is the temperature at which, okay, obviously you're gonna write this down properly, you're not gonna put at. Okay, so basically it's the temperature at which the vapor pressure is equal to the atmospheric pressure. Okay, back in the days, grade 9, well, yeah, we would say that boiling point, it is at the point where your liquids will turn into gases, but yeah, we have upgraded from that definition. Okay, so basically it's the temperature at which your vapor pressure is equal to your atmospheric pressure. And then 3.2.2, write down the independent variable for this investigation. For those who don't understand the difference between independent variable and dependent variable, basically independent means it is as it is. It doesn't depend on anyone or anything. Okay, for example, if you were to measure, like today's quite a hot day, okay, if you were to measure temperature against ice cream sales, your ice cream sales are dependent on the temperature. So the colder it is, the less your ice cream sales will be. The hotter it is, the more your ice cream sales will be. So your independent variable will be temperature, your dependent will be ice cream. In this case, let's say we had a graph, XY axis. Which one is dependent on which? Okay, the chain length, is it dependent on the temperature, or is the temperature dependent on the chain length? I would say the chain length is independent. Okay, so you are increasing, you are decreasing chain length, but the temperature is dependent on the chain length. So your temperature would be here on the y-axis. Okay, so your temperature would be on the y-axis, but your chain length okay, or number of moles, okay, because they are increasing definitely. Yeah, so your chain length, I would put it on the x-axis because it is as it is. And alkane, you know, butane, it is what it is. Pentane, it is what it is. But the longer your chain length becomes, the higher the temperature. So it's directly proportional, I would say. Okay. So what is the independent variable for this investigation? I would say chain length is your independent variable. Or if you would like, you could have said the number of moles, because as the number of moles increase, your temperature also increases. So that's the independent variable. Okay. Yeah, so chain length, or number of moles, or molar mass, whatever. Okay, now 3.2.3. Write down the type of van der Waals forces that occurs between these organic compounds. So for your alkanes, you would find London forces. So they're quite weak intermolecular forces. But yeah, London forces. And then 3.2.4. Is that the last one? Yes, quite a short question. It says write down the conclusion that can be drawn about the boiling point of straight chain alkanes. Okay, so we can say, looking at our graph there, that the longer, can even not use an arrow. So the longer the chain length, the higher your boiling point. Okay, and that's it. We're done with question 3. See you guys question 4. Hello there, welcome to MV Tutors, and thank you for joining me for question 4. We're still looking at chemistry, and then yeah, let's see what chemistry has in store for us. This was the Gauteng prelim written in September, and let's answer the questions that are following. Don't forget to like our videos, and don't forget to subscribe and click on the notification bell. Okay, so question 4. So it says most organic compounds can undergo different reactions to produce a variety of organic compounds. Some incomplete reactions are represented below. Okay, so we have a very busy diagram, and I want us to digest it, to rip it apart, see what's going on before you answer questions, right? We have some bit of time. How many marks is this? 14 marks. Okay, so let us see. Where do we start? We start here. Okay, I don't even know. Let me start there by 2-bromopropane, and then we'll work ourselves down. So 2-bromopropane, it is a haloalkane because there's a bromine there, bromine atom, and propane means we have 3 carbon atoms. So on the second one, that's where we have bromine, and yeah, the rest is hydrogen atoms. So 2-bromopropane, we know that it is a haloalkane. So what happens to it? Firstly, on on this side, we have C. Okay? And there is an addition of, okay, hydrogen bromide. And then we had propene prior to that. Okay? So propene, whether you put the double bond this side or the other side, it doesn't matter. No, 1, 2, 3, 4, yeah. Okay, so we have propene there, and that is an alkene. We're going to talk about the reactions soon. I just want to put things into perspective. And then from propene, we go to propane. So hydrogenation. So if the process is called hydrogenation, then we are adding hydrogen gas. Okay, so hydrogenation, that would be E. And then we have propane. 1, 2, 3. So that's just an alkane. Okay. And then from an alkane, we go back to 2-bromopropane. That would be reaction D. So we are adding a hydrohalogen. Yeah, we're adding a hydrohalogen. We're going back to the haloalkane. Okay, and now what do we have? Then we have a secondary alcohol. So going up, we have process A. And then going down, we have process B. And we have a secondary alcohol. Okay, so that secondary alcohol, okay, that is a nice tip. Because we've been dealing with 3 carbons here, if it's a secondary alcohol, it has to be the middle carbon. So that is where the OH group is. So the secondary alcohol, this is propanol. 2-propanol, propanol 2. No, there's no propanol 2. It's either 2-propanol or propan 2-ol. That's your secondary alcohol. Okay, secondary. And then we go from, from the haloalkane all the way down okay, maybe let me shorten, yeah, all the way down there, and that is F. So we went from a haloalkane all the way to an alcohol. Okay, now with a different colored pen, I will then let's choose green. Green looks nice. Okay, now let's see. For us to go from an alcohol to an alkene, do you realize that we eliminated something? Okay, so for us to have a double bond, so we had a single bond here, so we took out OH and we took out another H. Okay, let's just say we took out this H over here. And then we were left with 2 H's and yeah, the rest of the other hydrogen atoms. So for process A, to go from an alcohol to an alkene, we had to dehydrate it because we are removing water. Okay, so it is an elimination reaction. So A, we are eliminating. So elimination reaction, which is basically dehydration. Okay, and then from an alkene back to an alcohol, well, we are adding water, so we are hydrating. So it's an addition reaction. Addition reaction that we call hydration. And to do that, we need, what do you call this? A catalyst, which is concentrated sulfuric acid. Okay, concentrated sulfuric acid. All right, so we're done with that. Then we go from an alkene to a haloalkane, we added hydrogen bromide. Okay, so there we are gonna call that an addition reaction. Okay, we added, and it is yeah, it's an addition reaction. We are adding a haloalkane, so what do we, halogenation. Yes, yeah, we're adding a hydrogen and a halogen, so halogenation. Sometimes these things escape my mind. Okay, then yeah, an interesting thing though, when we go from an alkene to an alkane or a haloalkane, the question is, okay, we already know where the bromine atom is, but for you to determine where the bromine atom will go, because you don't know, will it go to the first carbon, will it go to the second carbon, you're going to use Markovnikov's rule. Markovnikov's rule. Okay? And basically Markovnikov's rule says, if you are not breaking, but you're adding to an alkene, and you don't know where the halogen is going to go, you need to look at the carbon with the most hydrogen atoms. Okay, so the carbon with the most hydrogen atoms, and that is basically when you want a major product. Okay, if you want a major product, so the carbon with the most hydrogen atoms will get the hydrogen. Okay, and then the other carbon with the least hydrogen atoms will get the bromine or the halogen in that case. So that is why your bromine is on the second carbon and not on the first. Okay, cool. Now let's go to D. So D, we went from an alkane to a haloalkane. Remember, alkanes are saturated, so you can't add to them. They're already filled. So for you to go from an alkane to a haloalkane, you had to substitute. Okay? So this is a substitution reaction. Okay, cool. Substitution. Now we go to E. So E, we had an alkene and we are adding hydrogen. Okay, H2. And that's basically called hydrogenation. So it's also an addition reaction called hydrogenation because you are adding only hydrogen. So addition reaction. And then we get an alkane. Okay, that makes sense. What am I missing? So for F, for this addition reaction, I think you might need heat or something. Yeah, so the addition of hydrogen. So you're gonna need heat, okay, to have that work out. And also a catalyst called platinum. Okay, then we go to, yeah, so now we go from the haloalkane to our alcohol, our secondary alcohol. Now what happened there? So basically, haloalkane, again, it is saturated. You go to the propan-2-ol, the secondary alcohol, it is also saturated. So for anything to happen, we need to do a substitution. Substitution reaction. Okay, and what type? So if we go, you can see that we took away bromine and we put there the OH group, okay, and then the hydrogen doesn't matter. So basically there was water involved in there. Okay, so this substitution reaction is called hydrolysis. And even for that, hydrolysis. Okay, wrote S on top of S. So yeah, so that's basically that. We have fully chewed and digested this thing and took it apart and what. So now let us answer the questions. Hopefully this will go by very quickly. So it says, consider reaction A, write down the reaction that takes place. We did talk about it. It's called an elimination reaction or dehydration. Okay, 4.2.1, it says reaction B represents a hydration reaction. Now define hydration reaction. So basically you are adding, because it is an addition reaction, so you are adding water to the compound. Okay, and then 4.2.2, write down the name or formula of the catalyst used for this reaction. So we could say concentrated sulfuric acid. You can write out concentrated. You can write out the name sulfuric acid, or you can just put the molecular formula, which is H2SO4. Okay, 4.3, during reaction C, so C is where we went from propene to bromopropane, from the alkene to the haloalkane. A specific rule is followed to determine the major product when hydrogen bromide is added. So basically that's where you use Markovnikov's rule, as I explained previously. And now it says 4.3.1, write down two conditions for this reaction. So this is an addition reaction. We are adding a hydrogen and halogen, so hydrohalogenation. So what are the two conditions for this reaction? Firstly, please no water, don't add any water. And this reaction, so another condition is this reaction is spontaneous, right? Spontaneous, therefore no catalyst required. Yeah guys, but I heard something. Apparently this has changed a bit in terms of no catalyst required. And then you need a strong acid. So I don't know, can you please confirm for me in the comment section? Because I normally use Mind the Gap textbook, so it says no water and no catalyst. So please just confirm if we do indeed need a strong acid as a catalyst. Okay, comment section, I'll be waiting for y'all so that going forward we don't repeat mistakes and we know what is updated and what not. Okay, 4.3.2 says use structural formulae and write down the balanced equation for this reaction. So we are going, we are going from propene, okay, which has 1, 2, 3. Whether you put the double bond here or you put it here, it doesn't matter. But choose one side, not both sides. Okay, so you have your hydrogen, and then there as well. Alright, and we are adding hydrogen bromide. Please don't write it as HBr. Remember, there is a bond between the hydrogen and the bromine atoms. Okay, and at the end we get our compound there. On the second carbon we have the bromine atom, and the rest is just hydrogen atoms. Alright, so that is the structural formulae of this balanced equation. If you want to check if it's balanced, make sure that the hydrogen atoms, the carbon atoms, and the bromine atom is the same on the left as it is on the right of the arrow. Okay, now 4.4. So it says, identify the type of reaction taking place at D. So D, looking at thing, it's the substitution reaction, and F, it's also substitution. So you can write substitution for both. Okay, if you want to be specific, substitution. If you want to be specific about 4.4.2, you could say hydrolysis. But both of them are substitution reactions. You'll get marks for saying substitution for both. Hydrolysis. Okay, and then 4.5, we're almost there. It says reaction E is a hydrogenation reaction because you're adding hydrogen, right? Now it says, write down the two reaction conditions for this reaction. So in this case, again, no water required. So that's one of the conditions, that's one of the reaction conditions. And another one would be that let me see. Oh yeah, we did put it. You need a catalyst, platinum. Yes, heat and platinum. So firstly, no water, and then heat, or you can indicate it. I don't know if they allow you just to put the enthalpy, but you need heat and platinum as your catalyst. Okay, that is 4.5.1. Yes, 4.5.1. Okay. And then 4.5.2. This reaction is widely used in industry. Okay, name one use of the hydrogenation. Yes, name one use of hydrogenation in the food industry. Well, I would say margarine. That's the one thing that came to mind. I'm not sure really what's the difference between margarine and butter, but I think there is a difference. Maybe you can tell me in the comment section. So yeah, basically it's to make margarine, and that's it. I'm sure there are other things as well, but that's the one thing I could think of in the food industry. And this concludes our lesson on organic chemistry. I hope you learned something, and please don't keep this information to yourself. Do tell others who are in matric, your classmates. Don't forget to like our videos and also subscribe to our channel. Okay, bye. Hello everyone, and welcome to MV Tutors. I'm Solo, and I'll be doing question 5 with you guys for chemistry. Yeah, it's been a minute yet again. Guys, it's a busy season. But let me not get into that. Let's just get straight into the question. Please don't forget to like our videos and also subscribe to our channel. And I hope that the preparations for maths are going well, because I know that soon you'll be writing, Friday to be precise. So all the best. Okay, now let us get crack-a-lacking. Question 5. So the graph below shows the change in potential energy for the reaction where limestone is changed into lime. So the balanced equation for the reaction is as given. All right, and we have our graph there of potential energy versus time, reaction coordinate. But yeah, so 5.1.1, it asks, is the forward reaction exothermic or endothermic? Well, if you look at it, you require a lot of energy to get this reactant to become this product, if you're looking at it in the forward direction. So because we require so much energy, it will be endothermic. Okay, endothermic. Now 5.1.2, calculate the heat of reaction for the forward reaction. Okay, so the heat of reaction is the same as saying enthalpy, right? And you will then choose, you know that the enthalpy is the energy of your products minus the energy of your reactants. Okay, so we have the energy of the products minus the energy of the reactants. And for your products, well, basically you have 420. I hope you can see it quite clearly there. So you have 420, that's where your products form, the energy that your products have formed. And reactants, well, at the beginning you have 0, right? So at the end, our enthalpy or heat of reaction would be 420 kilojoules per mole. Don't forget the unit, please. Okay, now 5.1.3. Write down the activation energy for the reverse reaction. Okay, so the activation energy, I wish I could write on this PDF, but let's just sketch a bit what's happening. If you were going to look at the activation energy for the forward reaction, which is endothermic, you would have taken what is it, 480, right, minus 0. Yeah, so yeah, activation energy. But in our case, in our case, the activation energy for the reverse reaction then is just this portion. Okay, in the reverse reaction. Okay, so reverse reaction will be exothermic because you only release a lot of energy once the product's formed. So this is the activation energy for the reverse reaction. So I'm going to say EA for activation energy. It's basically going to be 480, or the difference there, difference here. So it'll be 418 minus 420. And that will basically be 60 kilojoules per mole. Okay, just remove that, but yeah, you understand, right, how we got to the activation energy. And this is still early days, or not early days, but yeah, 1 mark, because they know you can read it off. Now we get to 5.2, and 5.2 has to do with the Boltzmann chart or graph. Before we even get to it, just to show you, if you want to understand it a little bit more, you can find it here. Once it loads, I actually do go into detail, the Maxwell-Boltzmann distribution. Okay, so if you go into it, I explain there what is what, the different scenarios you will get, and blah blah blah. Now the internet is failing me. Okay, so let us go back to our... Okay, what's happening? Okay, cool. Let us go back to the question. So it says, the following graph represents the number of particles that is on your y-axis against a specific amount of kinetic energy of the molecules. So that is your x-axis. The data for samples R and S was obtained at different temperatures, which affects the rate of reaction. Okay, so what kind of questions do we have? Now 5.2.1, define the term rate of reaction. So guys, I always say this, if you forget the definition, go to the formula, which you will get in your formula sheet, or some of the formulas are very easy. They don't actually give it to you, they expect you to know it. But the rate of reaction, basically, if you have like the change of concentration of your products or reactants over time, change in time, or the change in the number of moles, or the change in volume, yeah, so it can be the change in number of moles. Okay, let me not say equal to. Let me not lie. It's not equal to. Could be the change of concentration over time, or it could be the change in the number of moles over time, or it could be the change in volume over time, and so forth and so on. Okay, so I don't know if they have it in the formula sheet. Let's go have a look. But I feel like it's one of those simple formulas that they don't even write down. Yeah. No, they don't. Which is okay. So that is the rate of reaction. As soon as you hear rate, just know that there's a time factor to it. Okay. So yeah. So if we were to define the rate of reaction, well, it's basically the change in concentration of either reactants or products over time or per unit time. Okay. We want to see how quick or how slow reactants, products form, and so forth. So yeah, I think it's fine. I don't need to write that down fully. So you will write down the definition yourself. Okay. Then it says, what does the area to the right of line T represent? Okay. So if you have your Maxwell-Boltzmann diagram there, that line, that's basically indicative of activation energy. Okay, so on the left of the line T, you have particles there that are just existing. But to the right of T, the area there is where you have particles that have enough kinetic energy basically to form effective collisions, okay, because they have the activation energy. They have, yeah, if you have the activation energy, which is at line T, they have energy that is more than the activation energy, and therefore they can form useful collisions and products can be formed, okay. But let us see. So what does the area to the right of line T represent? Well, basically it represents particles that have enough energy, kinetic energy that is bigger than the activation energy, okay, to form effective collisions. So the smaller the area it is to the right of T, less particles actually do form products or have effective collision, okay. And then 5.2.3, it says, which sample was at a higher temperature? So is it R, is it S? Remember guys, whenever you increase temperature, your rate of reaction will increase, okay. And if your rate of reaction will increase, it means you're having a lot or more effective collisions. So meaning the area to the right of line T should be big, okay. So if I look at R, the area to the right of line T is actually smaller than S. So R is probably, yeah, while it's still a little bit cold, but as the temperature is increased, you get to S, okay. So S is the one, it has the higher temperature, okay. So sample S, yeah. They just said we can write R or S, but let's just say sample S. And then 5.2.4, it says explain the answer to question 5.2.3 by using the collision theory. Okay, so we know that S is the one with the higher temperature. Okay, how do we know that? We said the area to the right of line T is bigger. And how did that occur? Well, whenever you increase the temperature, all right, you are giving the particles energy, okay. So the higher the temperature, that results in an increase in kinetic energy of the particles, okay. And they continue to get energy to such a point that that energy is higher than the activation energy. And once it is higher than the activation energy, it goes past line T, and we have more effective collisions as such, okay. So higher temperature results in the energy of the particles, or the kinetic energy of the particles increasing, and them having more them being higher, the energy being higher than the activation energy, and then you start having effective collisions. So they start moving, right? They're already in motion because there is kinetic energy. So as such, then you have effective collision. I don't know if I'm leaving anything out, but yeah, it really has to do with that. Okay, and yeah, so the area, I guess you can then say the area to the right of T would increase. I don't know if it's necessary to put it, but yeah, area to the right of line T for sample S is bigger than that for R. Yeah, I'm seeing it's like 3 marks, so you can say something along those lines, okay. And then 5.3, so 5.3, 11 grams of magnesium ribbon reacts with 0.25 mole cubic decimeters hydrochloric acid solution at a temperature of 25 degrees according to the following balanced reaction. So this is basically where you can physically measure the rate of reaction, and for that, if you want to see the video for it to get a better explanation or to get more examples, you can visit our... Oh, you're already there though. Why is my internet so slow? Okay, let us get to it. Yeah, so basically you can go to the rates of reaction measuring, and I go through basically if you were to use... Where is this video playing? Oh man, when YouTube fails me. Let me pause and get it. Okay, I got the video. Technology. So basically I go through the rate of reaction measuring. How would you actually measure it yourself and see how fast or slow a reaction actually occurs, where you go from reactants to products. Okay, so you can catch that video out, but let us just answer the question here. Okay, so it says use the graph paper that is printed on the last page of the question paper and then plot a graph of these results. So you have time and volume of the hydrogen. Remember, as this reaction occurs, you have magnesium, you have hydrochloric acid solution. So once this reaction starts occurring, there you have bubbles that are forming, and that those bubbles will push against the syringe. Okay, and you'll take measurements and also the time as well. It went from one point to another, okay, until you get to a point where the reaction is completed. Okay, so now we need to plot time versus volume of hydrogen gas that is produced, and time is independent. Okay, it just happens. So it's always going to be on the x-axis, and then you have the volume of hydrogen that's going to be on the y-axis. So I'm going to just plot it quickly, and then we will discuss. Let me just pause and plot just to save time. Okay, so I've drawn the graph of these results. All right, and we can see it starts off being quite steep, and then it gets less steep until it gets to a point where this actually should be like flat. Okay, I decided to make it a dotted plot because it can be quite difficult to get a perfect curve. But yeah, so the last 2 points are the same value, which is 35 cubic centimeters. Now for 5.3.2, it says use the graph and explain what happened with the reaction between 2 and 3 minutes. So if you look then between 2 and 3 minutes, so it's at this point and at that point here, basically the reaction it slowed down, right? It started off when it's steep, it shows you how fast it's going, but the less steep it becomes, it means your reaction is slowing down. And between actually 2.5 and 3 minutes, it was done, it was complete, because we have a flat portion there. So for 1 mark, I would say the reaction slowed down. Okay, and then 5.2.3. It says, in the second experiment, the concentration of the hydrochloric acid changed from 0.25 mole per cubic decimeters to 1 mole per cubic decimeters. Draw a new curve on the same graph paper to show what effect it will have, and label the new curve X. So in this point, if you're going to increase the concentration of the hydrochloric acid, remember, an increase in concentration would mean that the reaction or the rate of the reaction will also increase, just like the same with the increase in temperature. Okay, so yeah, I'm gonna use maybe a purple line. So basically it's going to be steeper than we had it before. Okay, so it will start at 0 as well, and then it'll be more steeper. And because the reaction time is increased, it will have formed its products at a much quicker rate, so it'll be flat. It will start being flat from way before. So it might be at 35 up until yeah, Basically, I want it to be sort of like the same. It's difficult to plot, guys, but it will basically reach 35 much quicker. Okay, so I'm just gonna, we're leaving it there. So it will be much quicker because the rate is increasing. Okay, so we have plotted x. All right, last question. Assume the molar gas volume at 25 degrees Celsius, which is your standard temperature, is 24.47 cubic decimeters per mole. Calculate the volume of acid that was used in the first experiment when the reaction was completed. So remember, in the first experiment, we had 11 grams of magnesium ribbon with 0.25 mole per cubic decimeters of hydrochloric acid solution. Okay, so let's just put what we have. So the mass of magnesium was just 11 gram. Then we have the concentration of hydrochloric acid, and that's basically 0.25 mole per cubic decimeters. Okay, and now we need to calculate the volume of the hydrochloric acid. So if you remember, concentration is equal to number of moles over volume. So volume will be equal to number of moles over concentration. So we have the concentration of hydrochloric acid. We just need the number of mole for the hydrochloric acid. Okay, so let's see, what can we do? First of all, I think we should be calculating the number of moles of magnesium. Then we look at our equation, okay, our reaction equation, and see the ratio for the number of mole for magnesium as well as the number of mole for hydrochloric acid. I see for magnesium is 1 mole to 2 for hydrochloric acid. So let us calculate the number of mole for magnesium. So it's going to be the mass over the molar mass. And the mass, we said it's 11 gram. The molar mass, we need to check on the periodic table. And that is, so magnesium is element number 12, and that is 24. 24 grams per mole. Okay, so if we calculate that, what are we going to get?
Mama,
Yes, my baby.
I'm scared of the wolf. The wolves are a wolf.
The wolf. I'll be back. So my son thinks we have wolves. Yeah. Okay, so 11 divided by 24. I don't like this calculators that much. It just complicates things. So this is 0.458 mole. Okay, and remember, we have twice the number of mole for hydrochloric acid than we do for magnesium. So the number of mole for hydrochloric acid is basically twice the number of mole for magnesium, which is just this times 2, and that is 0.917 mole. Okay, now that we have the number of mole, we also have the concentration. So the volume then for hydrochloric acid will be the number of mole, which is 0.917. Please don't forget to keep that answer in the calculator so that your final answer is not watered down. Okay, and then the concentration was 0.25. Nah. So at the end, if I take that and divide it by 0.25, we are going to get 3.67 cubic decimeters. Just make sure, should be cubic decimeters because we're working with 0.25 mole per cubic decimeters. So yeah, 3.67. Ooh, it's not showing. 3.67 cubic decimeters. Just check. Yeah. Okay, and that is it. That is it, ladies and gents. Thank you so much for tuning in, and bye. Hello everyone, and welcome to MV Tutors. I'm Tsulu, and I'll be looking at question 6 with you. Please don't forget to like our videos and subscribe to our channel. And let's get right to it. So, the balanced equation below represents the reaction that reaches equilibrium in a sealed container. Okay, so we have nitrogen and hydrogen, which produces ammonia, and the reaction is exothermic because the enthalpy is less than 0. We have dynamic equilibrium, so the rate of the forward reaction will be the same as the rate of the reverse reaction. Okay, now it says to increase the yield of ammonia, adjustments are made to the temperature, pressure, and concentration of the equilibrium mixture. Okay, and we have the graph as indicated below. Alright, so yeah guys, if you're really struggling with this section of interpreting these graphs and how to work them out, please do check out on our playlist, still there with the chemistry, chemical equilibrium, Le Chatelier, common ion effect, Kc, and blah blah blah. So I go through these graphs and I tell you what happens if you have the number of moles versus time, concentration versus time. What else do I cover? There's something else. It's number of moles, concentration, and rate of reaction versus time. How do you deal with all those things when you have an increase in temperature, pressure, increase of concentration? If there's a catalyst, what happens? Okay, I go through that. So please do check it out. But let us begin and let's see what happens to produce more ammonia. Okay, so 6.1.1, it says identify the changes made to the equilibrium mixture at each of the following times. So at T1, we can see that there's a sharp increase of nitrogen gas, all right? And as a result, over time, gradually you see an increase in ammonia, which is what we want, right? So what would have happened there if you increase the concentration of ammonia? If you increase the concentration of nitrogen, think about the seesaw example. Nitrogen is going to be like a heavyweight, okay? So it will be unbalanced. So using the Chatelier's principle, and to make it more balanced, you are going to have to increase the products, which is ammonia, which is what we want. So we can see there, we had an increase in nitrogen gas. That is basically what happened, or increase in the concentration, increase in the concentration, because we need to say, is it concentration, is it temperature, is it pressure? So increase in concentration of nitrogen gas. Now 6.1.2, what happened at time 2? Well, I can see that nitrogen increased, okay, slightly, and then it decreased. And the same happens with hydrogen gas. Then you get ammonia increasing until it reaches a point of equilibrium where the concentration is more stable. So what happened there? This is a point where we are dealing with pressure, okay? So for us to get that increase in the ammonia, okay, with pressure you have to look at where the number of moles are the most and where they are the least. So for the reactant side, we have 1 mole of nitrogen and 3 moles of hydrogen, so you have 4 moles in total. And on the product side, you only have 2 moles of of ammonia. My head, my goodness. So we have 2 moles of ammonia. Now the question is, what happened for us to get an increase in ammonia? Remember, ammonia is only 2 mole. So there must have been an increase in pressure. Because what will increasing pressure do? When you increase pressure, you decrease the volume, right? Think about it. You have a balloon, it's quite big. As soon as you start applying pressure, the volume decreases, right? So you have an increase in pressure, which decreases the volume. Therefore, what is favored? The least moles are favored. And where are the least moles? They are on the product side, okay? So it becomes product favored. By increasing pressure, you want it to be product favored because we want to get more ammonia. So if you increase pressure, you're going to reduce the volume, and therefore you're going to look at, from your reactants and your products, where is the least volume, where are the least moles, and it's on the product side, so it will be definitely product favored. Okay, because ammonia has the least moles. We want more ammonia. With the least moles, the pressure needs to increase. Now 6.1.3, okay, we're left with 1. We've used up concentration, we've used up pressure. So we must be looking at temperature. But how do you know in general when there is an increase or decrease in temperature? Well, basically you know that because there is a gradual increase or a gradual decrease of concentration here, like over time. Okay, so it being gradual tells you, okay, fine, temperatures at play here. But what is actually happening? Was a temperature increase or was it decreased? Remember, this reaction is the forward reaction, that is, it is exothermic. The reverse reaction will be endothermic. So if we want more of ammonia, okay, we want it to be product favored, what are you going to do? Remember, forward reaction is exothermic, reverse reaction is endothermic. What favors what? An increase in temperature will favor the endothermic. A decrease in temperature will favor the exothermic. So the forward reaction is exothermic, okay? But if I want to have more of ammonia, I'm basically going to be increasing temperature. Increase in temperature favors the endothermic reaction. So that is what we're going to do to get a higher yield of ammonia. We will be increasing the temperature. Increase temperature of the system. Okay? And as a result, it will favor the endothermic reaction. Reverse favored. Okay, I don't need to write that. They just asked what happened. Sorry. I need the eraser. Okay, we leave it at that. Increase the temperature, which will, increase the yield of ammonia. Okay. And let us see. And we can see with ammonia. Okay, yeah. All right, question 6.2. It says, state Le Chatelier's principle in words. Okay, so basically, roughly spoken, it's basically to say that if there's a disturbance in your reaction, what Le Chatelier's principle says is it will try to correct itself, okay, to get back to a new state of equilibrium. That's basically the principle. But let us write it all in words and give the examiners what they want. So basically, when equilibrium in a closed system is disturbed, the system will find a new way. System will reinstate a new equilibrium. Okay, which will favor the reaction that opposes the disturbance. Okay, there's a C there, that will opposes the disturbance. So if ever there's a disturbance anyway, you reach a new equilibrium, and that's how we cope in life, right? Things happen to us, plans don't go according to plan, and we need to readjust and move on. So 6.3, the pressure of the reaction mixture in question 6.1 above is disturbed by increasing the volume of the sealed container. Okay, so previously the volume was decreased, so now we have increased the volume, which means that the pressure has reduced. Okay, now what's the question? Yeah, so the pressure is increased. No, the pressure is disturbed by increasing the volume. Okay, so it has been reduced. Now it says, how will the change above affect the yield of nitrogen? Okay, remember what I said? Actually, if you look at volume goes hand in hand with the number of moles. Okay, if you have high volume, you're going to look at where there are the number of moles are the most. Okay, it's on the reactant side, right? If you have reduced reduced volume, you're going to look at where the number of moles are the least, which is basically on the product side. But here we have increased volume and we have reduced pressure, so this will actually be reactant favored. Okay, and because it is reactant favored, okay, we're gonna have a decrease in ammonia, and that's what they asked. Write down only increase, decrease, or remain the same. So let's just stick to the question here. We're gonna put the decrease. And then 6.3.2 says we must explain. Use Le Chatelier's principle to explain the answer in question 1. So we are going to say the moment you increase the volume, all right, you will decrease pressure. Okay, by decreasing the pressure, decrease in pressure will therefore have this whole reaction favor the least moles. Sorry, the most moles. Most moles, which is on the reactant side. Okay, I hope it makes sense. So increase in volume will go with where you have the most moles. And then, that is the case. You increase the volume, you decrease the pressure, then the reactants in this case are favored. So therefore, reactant favored. So therefore, you are increasing the yield of nitrogen as well as hydrogen instead of ammonia. And that's where I would leave it. Okay. And then 6.4. You can either say, reactant favored or reverse. Favored. Sure, my handwriting. Anyway, now 6.4, 5 mole of nitrogen and 5 mole of hydrogen are now sealed in a 5 cubic decimeter empty container. Okay, sealed. So dynamic equilibrium will be occurring. So equilibrium is reached at 450 degrees. Upon analysis of the equilibrium mixture, it is found that the mass of ammonia is 20.4 grams. Calculate the value of the equilibrium constant at 450 degrees. Okay, remember, if you want to get equilibrium constant, we will be looking at the products, concentration of the products all over the concentration of the reactants. So here, we need to get the concentration of the products as well as that of the reactants. They give us the Kc formula here? Not really. So you must know the Kc formula. So I'm just going to pause and draw out the table, the rice table. That's what we're going to use. As soon as you see a lot of marks, you will have to use rice table. So I'm just going to pause, draw it, and then we're going to put in the missing values. Okay, I've drawn the table and now let us fill it in. As I was just reminded that we have gases here. Remember, pressure only applies to gases. So if you had liquids or aqueous solution, that does not apply. Pressure doesn't apply there. Okay, so anyway, this is our rice table. Now what they have given us is the initial amount of moles. Okay, let's put that in and then we'll put the ratios. Or let's just rather start with the ratios. Okay, so for your nitrogen, you have 1 mole. Okay, so we know that is 1. And then hydrogen, it's 1, 2, 3. And then our ammonia, we have 2 moles. Okay, so as we fill in the table, we need to follow those ratios. Very important. Okay, then the initial amount of moles. They do tell us here that we have 5 mole of nitrogen. We also have 5 mole of hydrogen. And remember, at the beginning, initially, we don't have a product yet. We just have the reactants which need to react and then form a product. So we will have 0 mole for ammonia. Okay, and now before we get to the change, we need to calculate something here. So they told us that equilibrium is reached at 450 degrees. Upon analysis of the equilibrium mixture, it is found that the mass of ammonia is 20,4 grams. Okay, so we need to then change that to the number of moles. Okay, so we have, I'm just going to say number of moles for ammonia, NH3 is equal to the mass over the molar mass. Okay, the mass is 20,4. Now we need to go and get for nitrogen. Okay, so nitrogen is the 7th element, which is 14. So we have 14 and we have 3 of hydrogen. Hydrogen should be 1. Okay, so we have essentially 20,4 divided by 17. Should be 1 comma something. Okay, so 20,4 divided by 17. Oh, nice. It's just 1,2. It's a clean number. 1,2 mole. Okay, so this 1,2 mole, where is it applicable? Okay, it will be applicable there by the change. Okay, so and this is for ammonia, right? 1,2 mole. That's where you put it. And now we need to get the respective number of moles during the change, okay, using the ratios. So if we had 1,2, sorry, that thing's flying all over me, 1,2 for ammonia. Okay, I'm just going to go to the easier one, which is 1. So for me to get to the number of mole for nitrogen during the change, I'm just going to divide 1,2 by 2, which I'm going to get is 0,6. So if I have 0,6 and I multiply it by 3, I'm going to get 1,8. Okay, so we have filled up the change. Okay, so R, ratio, I, initial amount of moles, C, the change, and then E, that's where we get to equilibrium. Now, because for us to form a product, the reactants are decreasing, okay, in order for the product to form. So we will be subtracting, okay, and here we'll be adding, basically because the product is increasing as the reactants are decreasing. So if we're going to take 5 and subtract 0,6, we're going to get what, 4,4. Okay, 4,4 mole. And then 5 minus 1,8, it's going to be 3,2, right? Yes. And then, okay, that's just going to be 1,2. Okay, now we have the number of moles at equilibrium. We need to get the number of, the concentration at equilibrium, because that is what we're going to need to calculate the Kc. Okay, so how do we get concentration? Remember, concentration is number of mole over volume. And did they give us volume? Yes, they did. They told us that the volume is 5 cubic decimeters. Okay, so we're going to take the number of moles and divide them by 5 throughout. So if we have 1,2 there and we divide it by 5, we're going to get 0,24. And then if we have 3,2 divided by 5, we're going to get 0,64. And if we have 4,4 divided by 5, that's 0,88. Okay, so those are the concentrations at equilibrium. Now we can then calculate the Kc value. So let's just write it again. Our Kc value, it's the concentration of products. And what is our product? It is ammonia. Concentration of ammonia. And we're going to take it to the power 2 because there are 2 moles there. And then nitrogen, and multiplied by hydrogen. We have 3 moles for hydrogen. So to the power 3. So the concentration of ammonia, we got it as 0,24. And that we square it. For nitrogen, we have 0,88. We're going to multiply it with the hydrogen, which is just 0,64. 0,64, and we're going to cube it. Now we can get, finally, the Kc value. Okay, so we have 0,24 squared all over 0,88 multiplied by 0,64 to the power 3. And our answer is 0,25. Yeah, 0,25. And do we have a unit? No, we don't. And that is it. Wow, and that is 9 marks. This wasn't so bad. I mean, we had a rough time during June, remember? So this prelim paper was not so bad. Okay, 6.5, we're almost there. The temperature is now increased to 700. Okay, what will happen to the value of Kc at this temperature once a new equilibrium was reached? Write down only, remains the same, increase or decrease. Remember the Kc value, guys. It's the concentration of products over the concentration of reactants. So we are particularly interested in what's happening to the reactants when the temperature is increased. Our reaction is exothermic. So exothermic favors the forward reaction. Okay, endothermic. Oh, and again, exothermic is linked with a decrease in temperature. Endothermic deals with the increase in temperature. So we have increased the temperature, meaning we are favoring the reverse reaction. We are favoring the reactants. Okay, and if we are favoring the reactants, means that the reactants will increase. And if reactants increase, remember Kc is inversely proportional to the concentration of the reactants. So if your reactants increase, then your Kc value will decrease. So if your reactants increase, your Kc value decreases. Okay, this increases, that decreases. So that is the answer you're going to give, decrease. And that concludes question 6. My husband will address question 7, and then we are going to finish this paper. Okay, left with question 8 and 9, then we're done. You can focus solely on maths. Okay, thank you.
Well, hello there. My name is Figa Manana, and we are still doing the prelims. This is the chemistry question number 7. All right, so let's get right into it. It says, define the term acid according to the Arrhenius theory. Okay, so we know that acid, according to this theory, let me just write 7.1. According to this theory, is a substance that produces hydronium ions. Okay, so the operative words there is that it produces hydronium ions. ions, and hydronium ions are like that. Okay, or if you don't want to say hydronium, you can say hydrogen ions. Hydrogen ions, it's the same thing, which is that. Cool. 7.2. Consider the following acid-base reactions. There's two of them, X and Y. Okay. From the reactions X and Y, identify the reaction that illustrates the Arrhenius theory. Okay, we just spoke about it, that it produces hydronium ions. So what we're looking for is a reaction that produced these hydronium ions or hydrogen ions. So if we look at this first one, X, there's a hydronium ion. So we can therefore conclude that probably X for sure. Let's see Y just to confirm. No hydronium ions there, no hydrogen ions. That's it. Okay, 7.2.2, write down a balanced equation for the hydrolysis of NH4 ions. Let's do that. Sorry, that's not what it is. It's supposed to be 7.2.2. This was 0.1. Okay, so here we go. Let's start again. Okay, it says write down a balanced equation for the hydrolysis of NH4 ions. Okay, so this is 7.2.2. This was 0.1. So hydrolysis, so we're going to add, what are we going to add? You guessed it, water. So we're going to have NH4 plus, and then we're adding water, H2O. Okay, it's reversible. And then what do we get to the side? We get hydronium ion plus, and then what's left? We're left with N, and we are left with 3 H's. Just to balance the equation, let's check if it's balanced. We got 1 N, 4 plus 2 H's. That's 6 this side. 3 plus 3, 6, 1 0, 1 0. Balanced. Okay, 7.2.3. Will the resultant solution from question 7.2.2 be acidic, basic, or neutral? Give a reason for your answer. Well, what did we produce? We produced hydronium ions, which means it's going to be, we just spoke about it, from the definition, it's going to be acidic because it produced hydronium ion. So acidic because it produced hydronium ions. Okay, let's do 7.3 now. A sodium hydroxide solution is prepared by dissolving 4 grams of sodium hydroxide in water to make a 500 centimeter cube solution. Calculate the concentration of sodium hydroxide. So what do we know? Always start with what you know. We know, or starting backwards, we know that concentration is given by the formula of number of moles over volume, isn't it so? Yes. So let's check this out. Do we have number of moles? No, we don't. So we need to solve number of moles. We have volume, we have volume. Okay, so now solving number of moles, what's the formula of number of moles? We know it's mass over molar mass. Are we given the mass? Let's check it out. We are given the mass, it's 4 grams. can we calculate the molar mass? Sure, we can, but let's put the numbers. Okay, let me just put the numbers here. So mass is gonna be 4 over molar mass. What are we dealing with? Sodium hydroxide. Sodium hydroxide is given by NaOH. Okay, so now if we go just scrolling down to this periodic table, what is Na? Na is 23, the molar mass. It's 23 plus oxygen. Let's check out oxygen. Oxygen is 16. There we go. Plus H, which is 1. This formula will then give us the number of moles. Question 7. It will give us the number of moles. So let's bring out a calculator. There we go. So on top we got 4, on the bottom it's 23 plus 16 plus 1 over 10. Let's change it to decimal, 0.1. Okay, so our number of moles is 0.1. We got that covered. So we can go back now to the formula for concentration, which is N over V. So it's 0.1 divided by, let's just go back and check our V. Our V was 500, so 500 divided by 1000. We always have to divide by 1000 if it's centimeter to decimeter. So it's 500 divided by 1000, and we get 0.5. Cool. It's just a conversion. So it's 0.5. Oh, we need the calculator again. Now we're gonna have 0.1 divided by 0.5, and there we go. Our answer is 0.2. And what is it? It's mole. Remember, this one was decimeter. We converted it to decimeter cubed. Okay, let's look at 7.3.2 now. During a titration, 12.5 centimeter cubed of sodium hydroxide solution neutralizes 25 centimeter cube of sulfuric acid solution according to the following balanced chemical equation. Okay, it's balanced, so that's good. Calculate the pH of this acid. Okay, what I can tell you is that this acid is what we call diprotic because there's 2 H's over there, hydronium ions. You'll see how that plays out, but let's just start with the question right now. So we'll start with this formula. You know that, well, here concentration is a number of moles over volume, but if I am to isolate the number of moles, then I'm gonna have concentration and volume is equals to number of moles. Now we're gonna do this for the acid, okay, and divided by same thing, but this time for the base. Okay, the base. All right. Okay, now let's just start putting in the numbers. Do we have concentration of the acid? That is what we need to calculate pH, because remember, pH has to do with an acid only. Okay, it's not pOH, it's pH. So that we need to solve for it. The volume for the acid, which one is the acid here? It's the 25. So it's going to be times 25 divided by the concentration of the base. We calculated it there. on top, 0.2 times the volume, it's going to be 12.5. Number of moles, well, we can see that from here, the balance equation, the acid is 1:2. So we're just gonna, we're normally interested on the ratio. It's 1:2. So for every 1 acid mole, 2 base ones. So there we go. Now all that's left for us to do is some mathematical gymnastics. So basically, if I take that side, it's going to be 0.2 times 12.5 divided by 2 times 25. Okay, let's bring out our calculator then. Let's put that 0.2 times 12.5. Downstairs it's 2 times 25, and then we get our answer is 0.05. Now what is this 0. It's the concentration of acid, or the concentration of the hydronium ions, or the hydrogen ions. So okay, but if you look at this acid, it's diprotic, which means it's got 2 H's. This 0.05 is for 1 hydronium ion, or 1 hydrogen ion. So we need to multiply it by 2 so that we get 2 of them, because it's diprotic. Remember, if there's 1 H in that acid, then it's monoprotic. If it's 2 H's, diprotic. If it's 3, it's triprotic, which means you'd multiply by 3 there. So our final answer is 1. So now remember the formula of pH. It is basically minus log of the hydrogen ion in this case, or the hydronium. Okay, so it's 0.1. If we put this in a calculator, let's do that. Where is my log? I can't find my log. Log 0.1. Let's close that, and I get -1. Oh, but there's a -1 over there, meaning we need to multiply with the -1, and we get a +1. Remember, in my calculator I didn't put this minus. If I did, I was going to get a +1. So the pH is +1. So final answer. Thank you so much. I really appreciate you watching this. I you know what, if you need extra help, I'm here, I'm available. Contact us. We'll be very happy to help you. Otherwise, all the best.
Hello everyone, and welcome to MV Tutors. I'm Solo, and I'll be looking at question 8 with you. We are finally completing the paper. Okay, so let us get right into it. And yeah, I hope maths went well. You're not really thinking about physics and chemistry, but once we're done with the maths, you are done with the maths. I still need to go get the paper and do the memo, and then we'll meet again for maths. But yeah, so let's see, we have a galvanic cell. So the galvanic cell represented in the diagram below consists of barium electrode dipped into barium nitrate solution and copper electrode dipped into copper nitrate solution. Assume that the cell operates under standard conditions. Now you remember the standard conditions, right? Temperature, pressure, concentration. Okay, So yes, we can see it there. Half cell A, half cell B. Now let's see 8.1. State two conditions or standard conditions under which this cell operates. Okay, so I mentioned temperature, pressure, as well as concentration. When we have gases, that's where we can deal with pressure. So in this case, let's just stick to the temperature and the concentration. So you know that the concentration has to be 1 mole per cubic decimeter. Okay, and then the other portion of it would be temperature. So if you are dealing with degrees Celsius, that would be 25 degrees Celsius. If you're dealing with Kelvin, I think it's 298. I like confusing it, 289, 298. But yeah, 298. All right. And then 8.2, which half cell, A or B, is the cathode? Okay, guys, you can see where the electrons are going, right? They are moving from the left all the way to the right. So in this case, since that's the case, reduction occurs at the cathode, red cat. Okay, so cathode will be half cell B. Okay, so right, only A or B. Okay, 8.3. Yo guys, I'm cooking and I think something is burning, but let's answer this question and then I'll go check the pots. Write down the half reaction that takes place in half cell A. So okay, we know that there's the barium electrode dipped into barium nitrate solution and the copper electrode dipped into copper nitrate solution. So how do you know which one is which? You're gonna see on your table the one that is likely to be more reduced. Okay, is it barium or is it copper? So the one that is more likely to be reduced will be at half cell A, leaving the other one for half cell will be half cell B, leaving the other one being half cell A, where oxidation occurs. Okay, so let's see between barium as well as copper. Oh, I see barium there at the bottom. So as soon as you see a negative number, just know that it is more likely to be oxidized. Okay, so barium has negative 2.9. Okay, and then if we go up looking for copper, we're looking for copper 2 plus 2 electrons. Now I see we have plus 0.34. So that means that it is more likely to be reduced, okay, at the cathode. So copper is for the cathode, barium is for the anode. Okay, so we can write the half cell reaction. And when you look at these standard reduction potential tables, okay, we are looking at the likelihood of these reactions being reduced. Okay, so if we have a positive value, you're going to write that equation with one arrow as it is. But if it is oxidized, you're going to have to write it in the reverse. For example, barium, we can see we have a negative value. And that means that, I'm thinking about the part. Barium, that means that it is more likely to be oxidized. Okay, so we have barium right there as a solid. I don't know if they will give you marks for putting the state, but yeah, I think let's just put it just to be safe. And then we have the ions, right? In aqueous solution, and we adding the 2 electrons. Okay, I'll be back. Okay, all is well. No one will be eating burnt food today. All right, so we have our half cell equation over there. Okay, let's try this again. Half reaction, that's what I meant. Okay, now 8.4. Write down the cell notation for this cell. Remember, we have a galvanic cell or voltaic cell. So you're going to have to show which one is the electrode, what happens once it's in solution, the salt bridge, what happens at the cathode, and so forth. So we have established that at half cell A, that is where oxidation occurs. That's the anode. Okay, we started off with our barium in a solid phase. Okay, right, as the electrode, and then it dissociates into its ions. Okay. I don't think they will penalize you if you don't put in the state as an aqueous solution and so forth. All right, then we have the salt bridge, which we indicate by 2 parallel vertical lines. Okay, and then we have our copper. Okay, the copper 2 plus ions with the 2 electrons, and then the copper electrode. Okay. All right, if this section, galvanic cells, or electrochemical cells, if it really confuses you, you can go to our playlist. We've covered it there. Okay, so we have written down the cell notation for the cell. Now 8.5, we need to calculate the EMF of the cell. All right, so let's go to our formula sheet. If you have forgotten, E cell, and you must have that theta there, which basically illustrates to you that we're working under standard conditions. Okay. Yeah, and then we have, I prefer describing what happens at the cathode, and then minus E anode. Cathode and anode in Afrikaans. Cathode and anode. Okay, so what happens at the cathode? That's where we have our copper, which is more likely to be reduced, and at the anode we have our barium, which is more likely to be oxidized. Okay, and copper, we need to look at the value of the EMF, which is 0, or the voltage, it's 0.34. Okay, and we subtract what happens at the anode. Barium, we have negative 2.9. And if we were to calculate that, geez, I forgot to activate my calculator. So 0.34 plus 2.9. So 4 plus 9 is, no, 4 plus 0 is 4, 3 plus 9 is 12, and 3.24 volts. Okay, yeah, 3.24 volts. I hope that is correct. Just it sucks sometimes how we're so dependent on our calculators, and some of these easy sums can dribble a person. Okay, so 8.6. How will each of the following changes influence the value of the cell's EMF as calculated in question 8.5? Okay, remember with the EMF that we got, basically it was the barium as well as the copper, and then we got the EMF, right? And now it says write down only increase, decrease, or remains the same. So ammonium sulfate is added to barium nitrate solution. Okay, so ammonium sulfate would look like, ammonium is NH4, which has a charge of +1, and sulfate is SO4 2-. Okay, so we need to double up on the NH4. Okay, so that's ammonium sulfate, and we are adding it to barium nitrate solution. We already have that, so barium nitrate. Nitrate has -1, the charge on it, and barium has 2+. So we need to double up on that. So what is going to happen to the EMF? This is a tricky one, to be honest, and I really want to know from you what you think, because what changes the cell's EMF would be temperature, which is what we're going to look at 8.6.2. Surface area, not so much. Concentration is the one thing that really plays a role in changing the cell's EMF. Okay, and that's when you use Le Chatelier to actually sort that out. So once you add ammonium sulfate, if only it sort of like increased either the content of barium, or yeah, I actually don't know. I don't know, because if you add the two, what's gonna happen is, so this one has a -1 charge, it's a +1 charge, this is a negative 2 minus charge, or 2 minus. This is a 2 plus, and that's going to be a minus. Okay, and so this will want to attract to that. Okay, and these would be your spectator ions. Then you'll be left with sulfate, okay, 2 minus, plus your barium, okay, 2 plus. All of that is an aqueous solution, something that I keep forgetting. Okay, and that would result in barium sulfate, which is like an insoluble product. Okay, so this would it would form a solute, which would just settle to the ground. So how will that change the EMF? I don't know, guys. Maybe it might remain the same. I honestly do not know. So all the chemists out there, those who've discussed with their teachers, please come to the comment section, and it's only 1 mark. That's the boring thing. So please do help a sister out. I'm not sure what would happen in that scenario. Like I said, I know if you increase temperature, if you add more of the concentration, I can give you an answer confidently. But with this one, since you're gonna form an insoluble product there, that's just probably gonna settle your barium sulfate, I feel like nothing will happen. So I'm just gonna go with remains the same, but I'm really open for correction. Yeah, please correct me so that I also know, and I also will ask my fellow chemical engineers to come help me out here. I should have probably asked them first before I attempted these questions. But anyway. Okay, and then what happens when the temperature of the solution is increased? The one thing about galvanic cells is they are exothermic by nature. Okay, so that's one thing. Galvanic cells, the reaction that occurs from chemical to electrical, that is exothermic. Okay, and also whenever you're dealing with a galvanic cell, when you are calculating, I forgot to mention, when you're calculating your E cell, you must always have a positive answer. If at any point you get a negative, you did something wrong, or you are dealing with an electrolytic cell, where you're always going to get a negative for electrolytic cell. So that's one of the things about it. So now the temperature is increased, and we know that temperature being increased favors the endothermic reaction. In this case, since we have an exothermic reaction, I believe that your EMF will decrease. Okay, right? Yeah, the cell's EMF will decrease at that point in time. And that's it, we're done. 14 marks. But please, 8.6.1 guidance will be required. I do enjoy reading your comments. Thank you so much for liking our video, subscribing to our channel, informing your classmates, and. I really appreciate it. Okay, bye. Hello everyone, and welcome to MV Tutors. I'm Solo, and I'm finishing this question paper with you guys. Finally, officially, we can put it down to rest. Alright, question 9. Don't forget to like our videos and subscribe to our channel. Don't forget to tell your classmates about this channel, and also the grade 11s will be in matric next year. Okay, pass on the baton. Alright, question 9. The diagram below shows an electrolytic cell used for the refining of copper in industry. Guys, these are the applications of the electrolytic cell. So if you don't know, we do have a YouTube, obviously you're there on the YouTube channel, we do have lessons, okay, chemistry lessons. Let me just show you, and so you can go have a look. Electrolytic cells, practical applications, where I do look at electroplating, purification of copper, the chloralkali industry, extraction of aluminium from bauxite, and okay, and an exam question. So I do go through that, so please feel free to do that. So yes, we are refining copper. Okay, this is a very simplified diagram, but it works either way. So now it says for question 9.1, state the energy conversion that takes place in this electrolytic cell. Okay, so here, because we have that power source over there, we will be taking it from electrical to chemical energy. Okay, question 9.1. Electrolytic cell goes from electrical energy to chemical energy, whereas with the galvanic cell or voltaic cell we go from chemical, because it happens spontaneously, from chemical to electrical energy. Okay, and then 9.2, what will be observed at the cathode? Okay, so at the cathode, that's where reduction occurs. At the anode, that is where oxidation occurs. Okay, so you have your copper 2 sulfate solution, and then we can see we have carbon electrodes, and they are carbon because they are chemically inert. They will not form part of this reaction. All right, so what happens at the anode is, I'm just going to use very loose terms. At the anode, as you have your electrons going, actually in this cell, I hope you've realized that we have the positive this side and the negative that side. Okay, so you know how electrons are flowing from positive to negative. So it'll be flowing in this direction. So this side, that's where we'll be having our cathode. Okay, where reduction occurs. And this side will be having our anode, where oxidation occurs. Okay, and ox and red cat. So yeah, so basically what happens is your electrons will be flowing from the positive terminal all the way to the negative side. Okay, and your copper, so copper this side will be oxidized until you have your copper ions. Okay, and this side, you take those copper ions and you form a refined or purified copper. So what will happen at the cathode? You will start seeing that the copper starts, let me close it up. You'll find that the copper starts actually surrounding the electrode there. Okay, so at the cathode, there'll be an increase in mass. I like saying that it'll be gaining weight gaining mass, while at the anode it's losing weight or losing mass. So increase in copper mass. Okay, and then 9.3. So write down the half reaction that takes place at the anode. So we have already discussed it. This is what we have. Okay, just gonna, yeah. So we had our copper there, and in the solution, which is copper sulfate, you will have your copper ions. Okay, let's just state the physical state, solid and aqueous solution. So that is what happens at the anode. Okay, and then please guys, whenever you do half reactions, do not put double arrows. Okay, this is like a no-no. Please do not put them in. It's like you are showing your exam and you don't really fully understand what's happening. Okay, you cannot put it in, because once it starts losing its weight or its mass and transferring it to the cathode side, that's what's going to happen. Okay, we're not having a reverse reaction here. It's just pretty much forward. It's like baking. Once you bake and you've used the ingredients, that's it. You can't take the cake and then decide you're gonna get back the original ingredients. Okay, now the last question, it says, what will happen to the color of the blue copper sulfate solution as the reaction progresses? So as it progresses, it will become lighter in color. So you'll have your blue, and then it will start getting a light blue until it becomes clear. So it will lighten, okay, to the point where it becomes clear. It's only one mark. Becomes clear. And that's it. We are officially done with this paper. We can then focus on maths again. I can't believe how time flies. Yeah, it's crazy. It's been a busy year. But yes, let's see each other at the maths final exam. I don't know when we're going to post it. Life is a bit busy, but we'll get it. We'll get there. So thank you so much. Enjoy the rest of your day.